But welcome everyone. So I would ask you, Andrea, to get in. And Andrea, let me introduce Andrea. Just a moment to open the bio. Okay, that's fine. Andrea is a civil engineering, PhD in environmental science at Wageningen University, the Netherlands. Is associate professor at the Department of Hydraulic and Environmental Engineering at the Federal University of Ceará, which is a beautiful place, by the way. And then Andrea is also now as editor-in-chief of Brazilian Association of Sanitary and Environmental Engineering, and member of editorial board of important journals. He has been working strongly in the areas of wastewater treatment, anaerobic digestion, environmental biotechnology, and water reuse. And it's also a consultant for research development agencies and some private companies also. So, André, thanks again for coming. It's a huge pleasure for us to have you here today. And the floor is yours.
Okay, thank you, Rodrigo, for the introduction and also for the invitation to talk about some of the research of our group, Environmental Technology Group, is conducting over the last 16 years since I returned to Brazil. So the talk of today will be about the possibilities and challenges for the application of the microaerobic process in the anaerobic treatment of segregated and non-segregated wastewater streams. So as Rodrigo mentioned, I'm based on the Federal University of Ceará and the Department of Hydraulic and Environmental Engineering. Okay, so my presentation will cover the fundamentals of the microaerobic treatment. And after all, I will present a few research that we conducted over sulfide removal, over pharmaceutical micropollutants removal in general, and also some other things that we discovered by using this kind of technology. First of all, the microaerobic treatment is presenting a lot of good opportunities for use in the anaerobic treatment, not only to remove H2S from the biogas, being a kind of in situ way of desulfurization, but also is showing very promising results on recalcitrant compound removal, such as BTX, such as micropollutants removal. So what is the microaerobic treatment? So first of all, I would like to come with the sulfur cycle in order to present how sulfur compounds, sulfide and hydrogen sulfide is formed in anaerobic treatments. So if we have sulfate present in the wastewater due to sulfate reducing bacteria, we produce sulfide, and once we apply the microaerobic treatment, we try to convert the sulfide formed upon sulfate reduction into elemental sulfur. So the idea behind this is to produce elemental sulfur, but also decreasing the hydrogen sulfide content in the biogas and also in the liquid phase. And we know that the hydrogen sulfide is the part of the sulfide that is causing the older problems in sewage and wastewater treatment plants. So if we have the sulfate reduction occurring in a USB reactor like this, we have the formation of sulfide, the dissolved sulfide, and due to the equilibrium, which is pH dependent, we have the formation and the transformation of part of this dissolved sulfide into hydrogen sulfide. And also due to the equilibrium between the hydrogen sulfide from the liquid phase, from the dissolved form and the gaseous form, we have the possibility and the recovery of the hydrogen sulfide in the form of biogas, and part of the hydrogen sulfide is discharged in the effluent together with the sulfide, the dissolved sulfide produced in the bioreactor. So the way that we apply microaerobic treatment, we assess different ways of microaeration, not only here in the headspace, but for instance, for pharmaceuticals, for micropollutants, the application of microaeration in the liquid phase is shown to be more interesting and efficient to remove these compounds from the wastewater. So the idea is we try to develop some strategies to remove both the sulfide from the liquid and from the gas phase, therefore decreasing the discharge of sulfur compounds to the rivers as effluent from the treatment plants. So if we think about the biogas composition, here we have basically the most part of biogas is methane. Also, some small part is carbon dioxide, CO2, and a small fraction of hydrogen sulfide, water vapor, ammonia, siloxanes, etc. And here, even though it's in a very low concentration, the problem is the odor perception of the human being is very low. So the odor sensibility level of the human being is for the hydrogen sulfide is 0.0004 ppm, which means that even a very small concentration, this compound is causing complaints in the treatment plants, and therefore ways to decrease the load of sulfide, hydrogen sulfide emissions is very important. So the idea is we combine strategies to decrease the H2S concentration from the biogas, but also to decrease the sulfide concentration from the effluent. The hydrogen sulfide is malodorous, is toxic, is corrosive, and the HS- is toxic to methanogens and harmful to anaerobic digestion process. If we think about sewage treatment, because sulfate concentration is very low, usually this concern is not very representative for sewage treatment. But if we think a more concentrated wastewater in terms of sulfate, maybe this toxicity of sulfide can be very hard in an anaerobic process, and therefore imposing a risk to the full conversion of organic matter. So the microaeration consists of the application of very small doses of oxygen, and this oxygen can be as a pure oxygen, or we apply atmospheric air, which contains 21% of oxygen. So this strategy is much cheaper compared to the pure oxygen introduction. On the other hand, is also presenting a kind of risk to the biogas formed, because it will decrease the methane concentration in the biogas. This is a technology that is using very low amount of oxygen, which means that the oxidation reduction potential, or P, in the bioreactor is in the same range of the traditional AD. So, and the measurement of this ORP is sometimes very difficult because of the low amount of oxygen introduced in the system. So if we think about the removal of hydrogen sulfide or dissolved sulfide, the activation of monooxygenases is not a very important aspect to be highlighted. But if we think about micropollutants removal or cyanobiotics removal in bioreactors, this activation, which is caused by this very low amount of oxygen, is already enough to activate the monooxygenase, and this is helping a lot to enhance the removal of these compounds in anaerobic treatments. So the oxygen introduced is not acting as a final electron acceptor. It's different when we talk about some traditional aerobic process in which the oxygen is indeed the final electron acceptor. Sulfide removal in both gas, which the results show good or excellent removals, and the liquid phase. For the liquid, we have moderate and low removals. The microaeration is also mentioned to improve, to help in the hydrolysis step of AD. As I mentioned, is helping to control the sulfide toxicity. Sometimes not that much, because as I will present, the microaeration is very efficient for the H2S form, but not for the dissolved fraction of the sulfide. It will decrease the corrosion problem inside and outside the reactor, because if we decrease the H2S concentration, which is causing the corrosion, we are helping this kind of control. And there's a very good way to control odor in sewage and wastewater treatment plants. So the thermodynamics behind this, if we think about the reaction, the idea is to combine the removal of 1 mole of H2S with half moles of oxygen to produce elemental sulfur. This is a very spontaneous process in terms of the thermodynamics or free energy of Gibbs. And depend on the form that we are considering this calculation, if it's in the H2S form or in the dissolved sulfide form, we have a small difference in terms of the delta G, but nonetheless, both are very negative values that therefore very spontaneous reactions. Okay, so these are the fundamentals of the technology, and now I'm going to present some of the results that we collected in some experiments here in the Federal University of Ceará. So first of all, I'd like to talk a bit more about the following of the research. Initially, we tried to use the microaerobic process for very low sulfate concentrations, because the previous research in other groups, there is a very strong group in Valladolid, the group of Professor Fernando Polanco, which did a lot of work in this field. Also, the group of Professor Janicek from Prague also conducted some previous research on microaerobic treatment, but both groups worked with the microaeration for anaerobic digesters, in solid waste, and the wastewaters with a very high sulfate concentrations. So the previous research was with these two conditions. And we initially tried to apply the microaerobic treatment for low sulfate concentrations, as we can find in sewage. So the results were very promising for the H2S removal. In another research, we tried to see the impact of the microaeration on BTX removal compared to methanogenic denitrifying sulfate reduction systems, and the results were very promising. And after that, we tried to see all the possibilities of to apply this kind of technology. Okay, so the idea when we started this research was to solve a problem that the low efficiency of the treatment for the dissolved sulfide. So we researched and we selected the way of applying autotrophic denitrification not only by using nitrite, but also using nitrate for sulfide removal. The stoichiometry is here. We see the dissolved sulfide with nitrate or nitrite, and is forming sulfate and also nitrogen gas and some water. Both processes are very negative, so thermodynamically spontaneous. And the idea is to see the different concentrations of sulfate and therefore sulfide formed, and also in terms of nitrite and nitrate concentration, to see the best combination of strategies together with microaeration to produce a system capable of removing both fractions of sulfide. So we applied here the nitrite, which is even more negative, therefore more spontaneous. The objective of this research was to evaluate the effect of autotrophic denitrification via nitrite associated with microaeration on dissolved and gaseous sulfide removal in an anaerobic reactor. So we run some experiments, and the different phases here that I'm going to show. The hydraulic retention time was 8 hours, which is more or less the HRT used in sewage treatment. The COD was around 1,000 milligrams per liter. We added ethanol as a model compound of carbon. We adopted the sulfate concentration of 100 milligrams per liter, which is the concentration usually found in sewage. And we varied the concentration of nitrite, and in some periods we applied microaeration, about 0.1 ml of air per minute. And sometimes we are normalizing or representing this value in terms of liters of oxygen per liters of wastewater. So it's both ways to present the microaerobic rate. Okay, the methods I'm showing here, so I will skip this and present these results. So here we have sulfur species in terms of load, and here we have the different phases. So as we can see, first of all, I'm going to present periods 2 and 3 compared. All the results I'm going to present compared to period 1. So here, when we introduce 50 milligrams per liter of nitrite, so we had the decrease of the dissolved sulfide of 9%, and the H2S decreased 49%. In period 3, the decrease when we applied 100 milligrams per liter, we decreased 89%, and the H2S was decreased 41%. All of them compared to period 1, which was the period that no nitrite, no microaeration was supplemented, therefore the conventional anaerobic condition. Okay, period 4, we applied 150 milligrams per liter. So there was a very good decrease. So all the HS minus the dissolved sulfide was removed, but the gaseous sulfide, the hydrogen sulfide, only decreased 36%. Period 5, when we applied both, combining nitrite addition and microaeration, we had 100% removal of sulfide. And in period 6, when we removed the sulfide supplementation, the reactor decreased the dissolved sulfide removal in 80%, but kept very high the H2S removal. And in period 7, when the condition was the same as applied in period 1, we had this kind of behavior, an increase of HS minus and H2S concentration compared to period 1. So here, as we can see clearly, that the application of nitrite removed the total load of sulfur species in 14% in period 2, in 83% in period 3, and 91% in period 4, and 100% in period 5. So the best strategy was this one, to combine the removal of both dissolved and gaseous phase of sulfide. Okay. Here we can see that in all cases, there was no difference in terms of COD removal, and also very small differences in terms of methane load, methane in terms of millimoles per day. It's important, and I'm not presenting here, to evaluate the methane content in the biogas, which must be higher than 40% for this biogas be used as a combustion fuel. Okay, these results resulted in a few papers that I'm presenting here. And here is a conclusion for this part of the research. Did nitrite addition remove both dissolved and gaseous sulfide? Yes, but more for the dissolved fraction. Did microaeration at the headspace enhance the gaseous sulfide removal? Yes, especially combined with the application of nitrite. Were organic matter removal and methane production in terms of millimole per day affected? No. And is the association of microaeration and nitrite addition a good strategy for complete sulfide removal in anaerobic reactors? Yes. Okay. And the last data that I'm going to present here is the application of microaerobic treatment on emerging micropollutants removal. So the first thing is the micropollutants removal is very hard and is very difficult to understand, and it's because the amount of micropollutants present in the wastewater is because of the different molecular structure, because of the different operational conditions applied in the research, and therefore some new approaches to try to enhance the removal of these compounds in low-cost wastewater treatment facilities must be investigated. So here we present some of the organic micropollutants here: estrogens, neurodrugs, antibiotics, anti-inflammatories, plasticides, antiseptic, and the concentration that they can be found in the sewage. So we also assessed this kind of system on personal care products removal, and we selected of a compound present in this category of organic micropollutants called parabens, and we assessed different concentrations of parabens, of methyl, ethyl, propyl, and butyl parabens, and the effect of microaeration in the removal of this kind of compound. Okay, so before we started this research, what we knew about? We knew that anaerobic process, the traditional anaerobic process, was not efficient on micropollutants removal. Most of the micropollutants, because of the low specific area, the absorption is lower compared to activated sludge process, and some co-metabolic process involved in micropollutants removal was not occurring under anaerobic conditions. Here we compare the removal of some micropollutants under anaerobic, aerobic, and anoxic conditions, and here we can see very diverse removal of the compounds, comparing conditions and structure. Therefore, is something very hard to establish a pattern and comprehend the full picture of micropollutants removal in treatment plants. So the researches shown that the temperature was not causing any difference in terms of kinetics or removal. the methanogenic activity in sewage treatment in USB reactor seems to improve. The higher the methanogenic activity, the higher the removal of OMPs. On the other hand, the methanogenic activity in anaerobic digesters treating sludge did not show any difference in terms of micropollutants removal. And the sludge retention time also did not show any difference when we compare high SRT and HRT of ADCSTR compared to USB reactor, that we know that the SRT is much higher. So also some research is showing that the characteristics of the compounds in terms of hydrophobicity and also in terms of molecular structure is interfering in the biotransformation of these compounds. So the metabolic versus co-metabolic reaction seems to be a co-metabolic reaction because of the concentration of these compounds is so low, it appears that is not sufficient to promote microbial growth. Therefore, a co-metabolic reaction must be the most interesting and active process in OMP removal in anaerobic and aerobic bioreactors. So we run some experiments on the use of microaerobic treatment on micropollutant removal. So these are the conditions applied. Here we can see a picture of the reactor. And we assessed in different stages here, increasing the concentration of oxygen in terms of atmospheric air here. So 1 ml per minute, 2, 4, 6, and decreasing to 1 in stage 6. Here for hormones and antibiotics, and here for parabens, the conditions applied. So I'm running off my time, but here is only to see the results we achieved for hormones, for plastifiers here, bisphenol A, and some drugs, diclofenac, trimethoprim, and sulfamethoxazole, under anaerobic conditions, therefore very low efficiencies in USB reactors. But when we apply microaerobic treatment, we have a very high removal compared to the previous stages. And if we observe the period in which we applied 4 ml per minute, we reached values above 9% for most of the compounds compared to anaerobic treatment. Very high capacity of OMP removal in anaerobic bioreactors. And the same trend can be observed for parabens. So low parabens removal under anaerobic conditions, but very high removals when we apply microaerobic treatment, even in the lowest oxygen air dosage applied in the system. Okay, and here in period 6, when we remove the microaeration, the efficiencies decreased sharply in the same range found in period 1, therefore showing that a microbial adaptation was not an issue for this increase in the removal efficiency. Okay, and we published some papers of this work. I'm also showing some of these papers in the presentation. And finally, some conclusions. Are OMP present in sewage and sewage sludge? Yes. Are OMPs biotransformed during wastewater treatment sludge digestion? Most of them, yes. In different percentage of removal, but most of them, yes. Do operational parameters affect OMP biotransformation? Yes, it will depend on the parameter. Temperature, no. Sludge age seems not to affect it. the methanogenic activity in sewage, but not in the digesters. The chemical structure, yes. The hydrophobicity, yes. But combining hydrophobicity, for instance, for triclosan, it's a very hydrophobic compound, therefore very well adsorbed into the biomass, but is not further biotransformed, which is very stable compound for microbial biotransformations under anaerobic conditions, for instance. And thus, microaeration enhance OMP's removal biotransformation. We showed that yes. So I would like to thank you again for the attention and for the invitation.